This is of seminal importance. This is very, very important, and the numerical value of H experimentally obtained is 6.626 into 10 to the power minus 34 जूल सेकेंड। अब आगे बात करेंगे, अगर इसको फ्रीक्वेंसी की फॉर्म में लिखना चाहें हम तो हम इजीली लिख सकते हैं और कुछ काम नहीं करना है। न्यू इज इक्वल्स टू सी लैम्डा रखना है बस हमें। न्यू इज इक्वल्स टू सी लैम्डा जब हम रखेंगे तो आराम से रखते जाइए, न्यू इज इक्वल्स टू सी लैम्डा, तो यू कैन इजीली ऑब्टेन व्हाट यू वांट टू राइट। सो रखिए न्यू इज इक्वल्स टू सी लैम्डा, तो व्हाट विल बी द रिजल्ट? तो आई एम डायरेक्टली राइटिंग इट फ्रॉम हियर, सो इट विल बी 8 pi hc over lambda to the power 5 1 over e to the power hc by lambda kt minus 1 in wavelength terms. Now our next purpose is from Planck radiation formula we want to derive the Wien's displacement law. So what we will do? We will just maximize maximum of du by d lambda. With respect to lambda we will simply maximize this thing. So this thing 8 pi is a constant, h is a constant, c is a constant. So 8 pi hc over lambda to the power 5 1 over e to the power hc by lambda kt minus 1 to the square. So now I want to differentiate it with lambda. So it will be 8 pi hc minus 5 over lambda to the power 6 minus hc over lambda kt e to the power hc over lambda kt over hc by lambda kt minus 1 का होल स्क्वायर hc by kt minus 1 by lambda स्क्वायर। तो लैम्डा टू द पावर 6 बाहर ले लिया, माइनस 5 और तो माइनस 1 और माइनस माइनस प्लस एच सी और लैम्डा के टी ठीक है। अब अगर इसे हम देखेंगे तो ये हो जाएगा 8 पाई एच सी ओवर लैम्डा 6 माइनस 5 1 माइनस ई टू द पावर माइनस एच सी बाई लैम्डा के टी प्लस एच सी ओवर लैम्डा के टी ई टू द पावर एच सी बाई लैम्डा के टी ओवर ई टू द पावर एच सी बाई लैम्डा के टी माइनस 1 का होल स्क्वायर 0। अब ये क्वांटिटी, केवल इस क्वांटिटी को हम देखेंगे तो अल्फा बाय लैम्डा एच सी बाई के टी इज इक्वल्स टू अल्फा। ओके, तो इसको हम देख सकते हैं अल्फा एच सी बाई के टी इज इक्वल्स टू अल्फा माइनस 5 1 minus e to the power minus alpha by lambda is equals to plus or alpha by lambda. Alpha by lambda is equals to 5 1 minus e to the power minus alpha by lambda आ गया. अब अल्फा बाय लैम्डा को, ये क्वांटिटी बहुत ही स्मॉल है तो इसको हम E मान सकते हैं. 5 माइनस E हो गया. अब इसको अगर इसमें हम रखेंगे तो अल्फा बाय लैम्डा 5 माइनस E, अगर हम इस इक्वेशन में रखते हैं तो हमारा हो जाएगा 5 माइनस E इज इक्वल्स टू 5 माइनस 5 1 माइनस E माइनस 5 प्लस E. अगर इसको हम देखेंगे तो हमारा निकल के आएगा लैम्डा इज इक्वल्स टू एच सी बाय 4.9663 बाय टी और 2.2898.9 into 10 to the power minus 6 over t. So lambda mt is equals to b. This b is 2898.9 into 10 to the power minus 6 millikelvin. This is called as the Wien's displacement constant. Now comes the photoelectric effect. The photoelectric effect provides a direct confirmation the energy quantization of light. It was discovered by Hertz in 1887. So electrons were ejected and we obtain a current called as photocurrent. When metals were irradiated with light, so if the frequency of the incident radiation, now there was few glitches in this. If the frequency of the incident radiation is smaller than a particular value and वो हर metal के लिए अलग अलग होगी, that depends on the properties of the metal. So no electron will be released and we will obtain no photocurrent. Number 2, no matter how much high is the intensity, the electron will be ejected instantly. Okay, how much low is the intensity will not be the factor. The electrons will be ejected instantly. The moment of the frequency of the radiation exceeds the threshold frequency, the electrons will be ejected instantly. It will not depend on intensity. At any frequency above nu zero, the number of electrons ejected will increase with the intensity. So after the threshold frequency is reached, for every frequency my number of electron released will increase will depend on intensity, but it does not depend on the light's frequency. And the kinetic energy of the ejected electron depends on the frequency. The Ke will depend on frequency but not on the intensity of the beam. The Ke of the ejected electron varies linearly with the incident frequency. The experimental finding explained within the purely classical context, notably the dependence of the threshold frequency. According to classical, any continuous amount of energy can be exchanged with the matter. That is, since intensity of any electronic wave is proportional to the square of its amplitude, any frequency with sufficient intensity can supply. If classically अगर हम बात करें तो कोई भी एनर्जी अगर हम sufficient energy amount में सप्लाई करें तो हमें इलेक्ट्रॉन दे देनी चाहिए. लेकिन इसमें थ्रेशोल्ड फ्रीक्वेंसी का कंसेप्ट निकल के आ रहा है. तो क्लासिकली वी वर नॉट एबल टू explain the photoelectric effect. And what about the weak force? With weak source also, if the frequency is higher than the threshold frequency, अगर threshold frequency से मेरा एनर्जी हाई है तो भी मेरे को इलेक्ट्रॉन मिल रहा है. The photoelectric effect would not take place for a long time, possibly for hours, until an electron gradually accumulated. अगर मेरी क्लासिकल थ्योरी में बिलीव करूं, अगर मेरे सोर्स वीक है तो तब तक मेरे को एनर्जी नहीं मिलेगी जब तक इलेक्ट्रॉन में इतनी एनर्जी में न डाल दूं अपने रेडिएशन के द्वारा कि वो उसको छोड़ के आ सके। लेकिन जो मेरे रिजल्ट थे वो मेरे को इंस्टेंट फ्लो ऑफ इलेक्ट्रॉन दे रहे थे व्हेन द इंसिडेंट रेडिएशन क्रॉसेस थ्रेशोल्ड एनर्जी। तो एक्सपेरिमेंट विल कंडक्टेड with the source that was so weak that it would have taken several hours for electron to accumulate the energy for its ejection, but लेकिन इंस्टेंट रिलीज हुआ इलेक्ट्रॉन का, तो मतलब जो क्लासिकल एक्सप्लेनेशन था वो गलत था। तो प्लैंक क्वांटाइजेशन रेडिएशन का फॉर्मूला तब तक आ चुका था, दैट वाज इन 1880 about 1900 something Planck radiation formula came, and inspired by that Einstein succeeded in giving the theoretical explanation of the dependence of photoelectric emission on the frequency of incident radiation. He assumed that light is made up of corpuscles. What Newton did earlier, Einstein simply came back onto it. When a beam of light frequency nu is incident on a particle, each photon transmits all energy h nu to an electron. There will be a complete energy transfer. H nu complete energy will be transferred to an electron near the surface in the process. The photon will be entirely absorbed. The electron will thus absorb energy only in quanta of energy h nu, 2h nu, 3h nu. When this energy is there, there will be complete absorption of energy. If h nu is larger than the metal's work function, that is the binding energy of the metal, you can say, then what will happen? That h nu is equal to work function plus kinetic energy. So it is like a law of conservation of energy. So when this h nu exceeds work function, then I will have kinetic energy. So kinetic energy can be written as kinetic energy is equals to h nu minus w. So for every metal there will be a property depending on the metal properties, that will be h nu minus h nu 0. The work function corresponds to my threshold frequency. Moreover, this relationship shows clearly why no electron can be ejected for nu is greater than nu 0 I need for ejection of photoelectron. So the ejected photoelectron acquire their kinetic energy from the excess energy. जो excess energy है वही काइनेटिक एनर्जी में चेंज होगी और इलेक्ट्रॉन का मूवमेंट ही मुझे करंट देगा। तब तक कोई फोटो करंट मेरे को नहीं मिलेगा जब तक मेरी फ्रीक्वेंसी, ये जो थ्रेशोल्ड फ्रीक्वेंसी है, इससे ज़्यादा नहीं होगी। द मैग्नीट्यूड ऑफ द फोटोइलेक्ट्रिक करंट जनरेटेड इज प्रोपोर्शनल टू विल बी प्रोपोर्शनल टू इंटेंसिटी ऑफ दिस रेडिएशन। तो जितने ज़्यादा मेरी इंटेंसिटी होगी उतने ज़्यादा इलेक्ट्रॉन्स को मैं हिट कर पाऊंगा, उतने ज़्यादा इलेक्ट्रॉन्स को मैं एनर्जी दे पाऊंगा और उतने ही ज़्यादा इलेक्ट्रॉन्स मेरे बाहर निकल के आएंगे। तो जो इंसिडेंट रेडिएशन का द स्पीड ऑफ द इलेक्ट्रॉन विल नॉट डिपेंड, but the number of electron will definitely depend, number of electrons coming out will depend on its intensity, because higher the intensity of this radiation, more the number of electrons will get free and more will be the photoelectric current thus generated is proportional to the intensity, yet the speed of the electrons, जो kinetic energy उसमें कोई चेंज नहीं आएगा, लेकिन जो मैग्नीट्यूड ऑफ फोटोइलेक्ट्रिक करंट क्यों बढ़ेगा? क्योंकि नंबर ऑफ इलेक्ट्रॉन जो है, चार्ज कैरियर्स जो बाहर आ रहे हैं वो बढ़ जाएंगे, तो इस कारण से उसका करंट बढ़ जाएगा अगर मैं इंटेंसिटी बढ़ा दूं एक फ्रीक्वेंसी पे। When the potential, the liberated electron will be prevented from reaching the anode, only those electrons with kinetic energy larger than EV will make it to the negative plate. So अगर मैं उसको रिवर्स करता हूं तो जो जिनकी एनर्जी EV, अगर V पोटेंशियल सपोज मैं लगा रहा हूँ across the tube, the liberated electron will be prevented from reaching the anode, only those electrons with kinetic energy EV will make it to the, तो इस तरीके से मैं फोटो करंट को मेजर करूंगा, तो उसको हम कहेंगे स्टॉपिंग पोटेंशियल। तो EV will be, VS will be called as stopping potential, that will be equal to H by E nu minus W by E, or H by E nu minus nu h nu 0 by E. So h by E nu minus nu 0. This will be called as Vs, called stopping potential. So if I plot Vs versus nu minus nu 0, that is the difference between incident frequency and threshold frequency, I will get a straight line. So the theory was given by Einstein in 1905, or practical explanation was given by Millikan, and one of the great scientists, Robert Millikan. So he gave an extensive collection of photoelectric data using different metals, and he obtained the value of Planck's constant correctly using the photoelectric effect experiment. That was regarding the photoelectric effect. Now come to the Compton effect. In 1923, Arthur Holly Compton provided another conclusive experiment regarding the particle aspect of radiation. By scattering X-ray of free electrons, he found that the wavelength of the scattered radiation is larger than the wavelength of the इंसिडेंट रेडिएशन. तो वेवलेंथ लार्ज है तो मतलब फ्रीक्वेंसी लो हुई, मतलब उसकी एनर्जी कम हो गई. दिस कैन बी assumed if and only if I assume that X-ray photons are behaving like particles and their collision are taking like particle collision, elastic particle collision. So X-ray scatter of free electron. According to classical physics, the incident and scattered radiation should have same wavelength. उनकी wavelength change नहीं होनी चाहिए थी. Classically, since the energy of the scattered radiation is too high to be absorbed by a free electron, the incident X-ray would provide an oscillatory electric field, but with an intensity that depends on intensity of the incident radiation. Compton succeeded his experimental results by explaining this as a conservation of energy and momentum by treating it as an elastic collision simply. So he treated it as simply an elastic collision. What he did, he took the momentum of the incident radiation, and this is momentum of the electron, because rest moment of the electron was 0, and this is the momentum of the scattered X-ray P prime. And if I put it, then electron momentum, that is recoil momentum of the electron, if I am going to take, so this will be P minus P prime. So if I am going to obtain this, this will be P square plus P prime square minus 2 P prime cos theta. So for this, this is equal to h nu by c, this is equals to h nu prime by c, P prime, and this separately. So I can write this as h square by c square nu square plus nu prime square minus 2 nu prime cos theta. This is my recoil momentum electron. Now if I take the energy, my electron before this was at complete rest. So what happened to my energy of the electron? So energy of the electron will E0 is equals to me c square. So now I write Pe c square plus me square c4. This I write now completely nu square plus nu prime square minus 2 nu prime cos theta plus me square c4 by h square. H I have taken as common. Okay. Now initial energy must be equal to final energy. Initial energy was h nu plus me c square is equals to h nu prime plus h under root nu square plus nu prime square minus 2 nu prime cos theta plus me square c to the power 4 by h square. So if I take this, then take nu minus nu prime to one side is equals to plus mec square by h is equals to square root of nu square plus nu prime square minus 2 nu prime cos theta plus me square c to the power 4 by h square. Okay. Now if I square both sides, this equation, if I square both sides, so nu minus nu prime ka whole square plus me square c to the power 4 by h square minus plus 2 nu minus nu prime me c square by h is equals to nu square plus nu prime square minus 2 nu prime cos theta plus m square c to the power 4 by h square. This cancels and this comes nu square plus nu prime square minus 2 nu prime is equals to plus 2 nu minus nu prime me c square by h equals to minus 2 nu prime cos theta. So this cancels. So if this comes here as 2 nu prime 1 minus cos theta nu prime 1 minus cos theta is equals to 2 nu minus nu prime me c square by h. So if I do this, 2 से 2 cancel and if I take it here 1 minus cos theta h by me c is equals to nu prime minus nu over c, ठीक है. तो ये h by me c 1 minus cos theta is equals to lambda prime minus lambda. This gives delta lambda. Delta lambda is called as the Compton shift. Compton shift comes out as h by mec 1 minus cos theta. I can also write 1 minus cos theta as 2 h by mec h by mec sin square theta by 2. So I can also write it as if I take it as sin square theta by 2 sin square theta by 2. I think there is no harm in doing this. 2 sin square theta by 2 is completely fine. 2h mec me I think it's fine now up to here. And now I can also write in terms of Compton wavelength lambda c h cross by mec, where h is lambda by h by 2 pi is called as the Compton wavelength, whose value is 3.86 into 10 to the power minus 13 meter. So today we discussed about the photoelectric effect, the black body radiation and the Compton effect, and then how the quantum mechanics was developed. Thank you very much.